Hey everybody, in this video we're going to talk about oxidation states, sometimes called oxidation numbers, what they are and how to determine them. Let's begin with what they are. Oxidation states are simply numbers. Each atom is going to get its own number, its own oxidation state, and that number is going to tell you how many electrons that this atom has lost or gained in comparison to its normal elemental state. The best way to understand that is with some examples. Imagine, if you will, a normal elemental iron atom, represented here with this circle labeled Fe. If that iron atom lost one negative electron and then lost a second negative electron, after that loss has occurred, you're going to have the exact same iron atom, except now it's lost two negative particles. This iron atom now has an oxidation state of +2. We often represent these changes with sort of like a chemical reaction that shows what's taking place, where you've got the Fe before it's lost its electrons, represented by this oxidation state of 0. That's the normal elemental iron. And then afterwards, after it loses the 2 electrons, its oxidation state changes to a +2. In that chemical equation, you can show that the electrons are lost by putting them on the product side, 2E- to represent the loss of 2 electrons. The same thing can happen when atoms gain electrons. Here, let's talk about chlorine. We've got just a typical chlorine atom. If that chlorine atom were to gain 1 electron, then that means its oxidation state is going to change to a -1, because now that atom has 1 extra negative particle. In terms of the equation version of this, you've got your Cl that exists before it's gained an electron with an oxidation state of 0. After it gains that electron, it changes to a -1, and the electron, since it's being gained, we're going to put it on the reactant side this time to show that it's essentially given to or absorbed by that original Cl atom. The point is, these -1s and +2s are there to tell me how many electrons have been lost or gained. The last part of this is going to be, how do you determine these numbers? We've got a set of rules to follow here, starting with number 1 that says any uncombined atom, that means like not bonded to something else, that's in its elemental state, has an oxidation number of 0. So, like the one we just saw, if you see elemental iron, which is just solid iron metal, because this iron is not bonded to any other elements, you'll know that its oxidation state is going to be 0. The same is going to apply for your diatomic elements like hydrogen gas. Even though hydrogen is technically bonded to another atom here, since that other atom is itself H2, this still will count as an oxidation number of 0. If you see any ions, the charges of those ions are going to be the same as the oxidation numbers of those elements. In other words, if you saw an ionic compound like sodium fluoride, like all ionic compounds, the atoms inside of it are ions, and those ions have charges. Like Na is a +1 charge. That +1 charge is the oxidation state of the sodium. Same thing with the fluoride, its charge is -1. That charge is also the oxidation state of the fluoride. Rules 3, 4, and 5 summarize some atoms that very commonly have the same oxidation state with very few exceptions. One of them is fluorine, which is pretty much always a -1, like we just saw in sodium fluoride. Oxygen is another one. It's almost always -2. There's one relatively common exception, a type of compound called a peroxide, where it's not a -2, it's actually a -1. You'll know it's a peroxide because you'll see the word peroxide in the name of the compound. The last one of these is that hydrogen is almost always a +1, with one relatively common exception, a substance called a metal hydride, where the hydrogen is forced to be a -1. That's going to look like this, NaH. This is a metal hydride because you've got a metal, like sodium, bonded to the hydrogen. In this case, the metal takes the priority to be the +1 charge. Since hydrogen now can't be the +1, it's forced to be the -1, and that's how it'll work for metal hydrides. Last but not least, and probably the most helpful rule, is knowing that the sum of all the oxidation numbers will equal the total charge of that species. For example, if you saw MgF2, magnesium's oxidation state is going to be +2. Fluoride's, of course, is going to be -1. If you added up the totals of all those oxidation states, you've got the Mg that's a +2 combined with or added to the two -1s, right? So each fluorine is -1, and those two -1s collectively bring in a total of -2. If you add all those totals together, you'll notice that they add up to 0, which was the overall charge of MgF2 from the beginning. It's a very useful rule when determining oxidation states yourself. So that wraps it up for this video on oxidation states or oxidation numbers. Thanks a lot for watching.